Tonight's the first night in a 3-part series on classifying chemical reactions. You have learned in class, using the POGL activity, that we have synthesis, decomposition, single replacement, and double replacement reactions. You also learned a 5th type, combustion reactions, right at the end. What I'd like you to do is, in your foldable, I would like you to go to your precipitation reactions tab. You can write above it and you can write behind that tab in order to take your notes tonight. One thing that I want you to keep in mind is that our precipitation reactions are a type of double displacement or double replacement reaction. We will learn about acids and bases in another lecture. The driving force for a precipitation reaction is the formation of a precipitate or a solid when 2 aqueous chemicals are mixed together and react. Some of you were wondering how we go about predicting the products when you got to the last part of the POGL activity and you struggled with it. So let's see what maybe needs to be cleared up. When we predict our products, the anions switch partners. Most ionic compounds dissociate in water. How are we supposed to know that? We actually learned that when we learned how to classify chemical compounds. We learned that ionic compounds carry a charge in water through our conductivity meter. This told us that the ions had to have dissociated or separated from one another. How do we know which product is going to be a precipitate, since we're dealing with precipitation reactions? I asked you last week to investigate solubility rules. If you have not done that yet, you need to look at page 178, either the table 7.1, or the figure 7.3, both which tell us whether or not a product is a precipitate. You need to copy one or the other down and start studying that, because you do need to know these rules. Okay, let's take a look at our first example. Here on page 174, we have a figure where we are allowed to see that we have two aqueous solutions. Here's a clear liquid one, and we're told that yellow potassium chromate solution. So this is the potassium chromate. So then this leaves us to believe that this is the barium nitrate, okay, colorless. When they come together, we get this gelatinous precipitate. And you've seen this in the lab yourself when you've created a precipitate before. We are asked here or I am telling you that we're going to figure out what that precipitate is, using what we know so far. So let's take a look here. We know that we have the potassium chromate, that's yellow. So when we write the formula for that, we have K2CrO4, and we know that that's aqueous, and we're mixing with that barium nitrate. Okay? Okay. Now, we know a precipitate is formed here. So, we need to figure out what that precipitate is, don't we? Well, when we work on that, we have to look and see what our reactants are. You can tell here that we have 2 compounds reacting. What kind of reaction always involves 2 compounds reacting and doesn't have a hydrocarbon? If you guessed a double displacement, you're right. And since this is the lecture on that, you were right that way too. So in a double displacement reaction, we learned that the anions switch partners. So we're going to bring the nitrate over to the potassium, and the chromate will go with the barium. So let's see how we do that. If you recall from your POGL, you have to look up the charges and re-crisscross. Potassium is a +1, and nitrate is a -1. And then barium and chromate are both +2 and -2. But this doesn't help us figure out the physical states, does it? Nope, we need something else. So let's take a look at your book. If you take a look at the diagram here, we see that all nitrate salts are soluble and our potassium is soluble. Basically all alkali metals. If we take a look at the rules, most salts of sodium, potassium, and ammonium are soluble. So that indicates to us that the nitrate is most likely going to be soluble. So we're going to place an AQ here. So that leaves us with barium chromate as being our precipitate, which is correct. But let's take a look at why. Unfortunately, with our solubility rules, they're not end-all be-all. If you look here, you will not find anything about chromate. So that tends to be a problem. But since we already identified the aqueous solution, and we know because we can physically see a precipitate is formed, that's what allows us to say that the barium chromate is going to be a solid. Oops, sorry about that. So we'll move that up here. We do have to look for balancing, and as you can see, we are not balanced, so we need to put a 2 coefficient right in front of the potassium nitrate. When we do that, we have a balanced equation for our figure in our book. Okay, pause the video and copy down the equation, or excuse me, the question. All right, let's take a look. So in this particular problem, we have sodium sulfide, so Na2S, and it gets mixed with cuprous nitrate and some precipitate results. So again, based on what we know so far, because we have two compounds reacting together and they're both aqueous solutions, we know that this is going to be a double displacement reaction. So when we know that, that tells us we switch our anions. So the sodium and the nitrate are going to come together. Let me shrink this down a little bit. Okay, so sodium and nitrate are going to come together. So we get sodium nitrate. They're both +1, -1. And the cuprous ion and the sulfide ion are going to come together. And we have this. So now we have to decide what the precipitate is. So when we look at our solubility chart here, again we see that the rules don't change. Nitrate salts are soluble, and sodium salts tend to be soluble. So definitely sodium nitrate is going to be soluble. If we take a look at the insoluble compounds on the picture here, you'll see that sulfide ions tend to be insoluble. So that confirms that the cuprous sulfide is going to be our precipitate. Oops, wrong thing. Sorry, guys. Okay, so we write that this is going to be our solid, our precipitate, and then the nitrate's going to be left in solution because it's soluble. Sodium nitrate is soluble. It's left in solution as ions, and so we label it as aqueous. The last thing we need to do is double check that we're balanced. So when you take a look and we need 2 sodium nitrates and 2 cupric nitrates in order to get this to balance. Please take a moment and write down this problem. Here again, we're starting off with 2 aqueous solutions, sodium phosphate gets mixed with barium chloride, and a precipitate results. So again, we know from what we've learned through our POGL that when we've got two aqueous solutions reacting, it's going to be a double displacement, so the anions are going to switch. So that's a quick fix for us. We know we have to re-crisscross our charges. So sodium and chlorine are going to come together to form sodium chloride. And the barium and phosphate will come together as barium phosphate here. And now we have to take a look at our solubility chart. And when we take a look here, we know that our sodium ion, our sodium compounds tend to be aqueous, as well as our halogens, chlorine, bromine, and iodine. They tend to be aqueous as well. Plus, we all know that sodium chloride is table salt and it is soluble in water. Now, just to confirm for our barium phosphate, our insoluble compounds tend to contain phosphate here, okay? So that helps us. We can also kind of see that barium tends to be exceptions to the rule, but there are no exceptions here. So our phosphate is going to be considered to be insoluble, which tells us then that our barium phosphate is in fact our solid like we thought, simply because we knew that sodium chloride dissolves, which makes it aqueous, and the fact that we know we had a precipitate. If you know you have a precipitate and you can rule out one of the products as being soluble, then you know the other product must be the precipitate. And that's okay. That assumption needs to be made in some cases, like the first example that we saw tonight. The last thing we are left to do here is to balance our equation. And when we do that, we need 2 sodium phosphates and 3 barium chlorides and 6 sodium chlorides in order to balance this equation.